Okay, let's get started. Wait, let me sure. Okay, so any questions so far? This time we go over most of the Shor's algorithm. Okay, and let's have a quick review. So the Shor's algorithm by number three. So when we want to factor a number, a good way to find it is doing this period finding problem or order finding problem. So the idea is that you got a big number n, and you want to factor it, then you can do it by solving this problem. So if you get an arbitrary x that's coprime to n, to your big N, then you want to find this period of x related to n. That is, you want to keep multiplying x by itself and see when does it go back to 1 mod n. Okay. So you want to find the smallest r such that x to the r equals to 1 mod n. Okay. And here we have the example. We have n equal to 3 and n equal to 7 and x equal to 3, and we see the period is 6 because you keep multiplying x by itself, and when you have x to the 6, then this thing is equivalent to 1 mod n. Okay. And so you found out that if we keep doing this multiplication mod n thing and keep multiplying x, then they will be cycling through these 6 numbers. Okay. So it will be 3, 2, 6, 4, 5, 1, 3, 2, 6, 4, 5, 1. It will be keep going here. And okay, so this is classically why are we having the echo? Okay, maybe let me adjust this. Okay, hello. Maybe this is better. Hello. Okay, yeah. So here we have an order here. So if you keep multiplying x by itself and keep going doing the multiplication by mod n, then you will cycle through this number. Okay, so this cyclic structure gives us let us to give a phase quantum algorithm to solve this. Okay, so the quantum part of the Shor's algorithm is to use phase estimation to solve this order finding problem, because we found out that if you're starting from 1 and keep multiplying x, then they will be cycling through this 6 number. And so we think about this multiplication unitary, that is a unitary that's labeled by x, and so you will multiply some number with x. Okay. So multiply some number with x mod n. So if ux apply on some y, then it becomes xy mod n. So we think about this unitary, and we find out that if we do phase estimation on it, you will find, well, you will not find directly, but you will find a very good information about the order R here. And the idea is that because this ux is a cyclic permutation between those 6 states or the R states, and because it's a cyclic permutation among those R states, then there will be R eigenvalues of this U kind of in this R-dimensional space. Okay? And here we have eigenvalues, so it's very very relative to Fourier transform. So the first eigenstate is you just take all those 6 states in equal superposition, then you see that you apply the ux on it, or you multiply everything by 3, then you see it's a cyclic permutation between all of them. But the addition has addition don't care about order, so it's still the same state. Or you can apply some omega before those states, where omega is e to the 2 pi divided by order r. And so you see you have those u0 to ur minus 1. And their corresponding eigenvalue will be e to the 2 pi I will be this omega 6 to this number s here, where omega 6 is the 6th root of 1, and omega 6 is the 6th root of 1, and s is the label here. So s is 0, 1, 2, 3, 2, 5. So you see S go from 0 to R minus 1. And you have R stay here. And you have omega to the some power. Okay. And omega to the some power, you write down it explicitly is omega to the e to the minus 2 pi I R over R and S times K. Where K is the number here. So K equal to 1, 2, 3, 4, 5, 6 here. Okay. And anyway, then we find out that the eigenvalue is e to the 2 pi S over R. And in terms of phase estimation, the phase we found will be S over R. Okay. So we take any one of those states into phase estimation with respect to this multiplication unitary UX, then you will get S over R. But we found out but it's hard to construct those states. So to construct those states, you actually need to know R to get the superposition of those. So it's not possible, but we can actually get the superposition of all those states. So we found out that if you add all those states together, then every register cancel out except the R1. Okay. Excuse me. Okay. The R1 where you have. Okay. So maybe let me make this even smaller. Okay. Where you get R1, so you get 1, 1, 1, 1, 1 here. Okay. Okay. So you add them together, then you only get 1. Okay. So 1 is the equal superposition of all those states. So if you use 1 as your eigenstate in your phase estimation, then you get a uniformly random distribution over those S over R, or uniform distribution over those R, S. So you get a uniform S, and so you get some S over R. Okay. And then we see that this S over R, but there are tricky points that we need to solve this. So you want to do this phase estimation, so you want to do this UX very efficiently. You need to do multiplication exponentially fast, and that's how we do repeated squaring. And then S over R, so you get S over R, and but our phase estimation has error, so you don't get the exact fraction here. So you need to guess this fraction, and that's how you use where we use a continuous fraction algorithm. And finally, S and R might have some coprime. So when you get S over R, you don't know R exactly, because you get 2 over 6 actually equal to 1 over 3. So your R, you will think it's 3 instead of 6. And to do this, you draw multiple S over R and take the least common multiplier of those R. Okay. And so we see those details, and finally, okay, and finally now we believe that we can do order finding. Okay, so any questions so far? So now we believe we can do order finding, and then we go back to number theory and we show how to do factoring. So to do factoring, okay. So now we can do factoring and use order finding. Sorry, now we can do order finding, and to use order finding to do factoring, what we do is we pick random x and calculate the order. Okay. And now there are a lot of probability here. So first you need to have the order, not a number. So you need an even number order, and you have an even number order, then then you need to get lucky, so that, and your constant probability you are lucky, so that xr over 2 minus 1 will have a factor with n. Okay. So if that's the case, so you check whether that's the case by calculating the GCD between xr over 2 minus 1 and n. Okay. And this algorithm is fast, is something you probably learn in elementary school. You just keep dividing two numbers sequentially. Okay. It's called Euclid's algorithm. Okay. And okay, so that's about the review. And now to go to the detailed factoring algorithm, first we have just a theorem to say that all the constant probability work out. So here we have two criteria to have things work out. Okay. So we need, so we say we have a number that's a composite number. So it has a whole bunch of prime to some power multiplying together. Okay. And if it satisfies two criteria, first is it's an odd number, and second is it has more than two different prime factor. And then basically we have a lot of words here, but basically that says the probability. So those two probability uh, uh, will be constant. So guys, we can say good thing or bad thing. So I guess that's the least positive part. So yeah. So the good part is greater or equal to constant. So the probability that R is even, and also that you find the GCD between xr over 2 minus 1 and n. So this is non-trivial. So the probability that you draw x that's good enough such that you get factor through this calculation is greater or equal to a constant. But yeah, so there are different ways, I think. Well, I guess the constant is from number 3. But yeah, book calculation is a bit weird, but anyway, it will be a constant. Something about 3 over 8. Okay. Okay. And now have a theorem, then we can finally write down the detailed factoring algorithm. So we write down every detail to deal with the weird edge case. Okay. So the heart of this algorithm is still need to do order finding. So we'll draw random x and do order finding to find R. Okay. But now we have a lot of different details to deal with things that basically this theorem cannot handle. Okay. So the first thing you need to do is you need to check n is a number, and basically you just divide n by 2. Okay. So divide n by 2, and so you check whether 2 is a factor of n. And if the 2 is a factor of n, then very good, you have solved your factoring. Okay. Okay. So 2 is so after this step, then n is not a multiple of 2, so it's a odd number. So we have first thing check. Then second thing, we need to show that n has more than 2 prime factor. Okay, so this is actually not trivial, although it seems like kind of trivial. And well, you want n equal to pq, then you want 2 different pq. But the thing is, n might be p times p or p times p times p. So it can be that n equal to 1 and n is still not a prime number. Okay. Okay, so we need to check n is not just 1 prime to some number. Okay, and how we do this is basically we take a square root, a cubic root, all the way to 1 over L's cube root. Okay, and so there are all of those things to check, and I think to calculate each one of them, you need to do about L squared calculation. So totally you need the order L cube calculation. That is still in our time budget. And once again, L is the logarithm of n. Okay. And okay, so small calculation here. You only need to do up to n to the 1 L squared, n to the 1 L, because this thing, because the smallest possible factor is smallest possible factor is 2. Okay, and then 2 to L equal to n. So yeah. So for this thing to be at least 2, then this is at most 1 over L. Okay. 2 to L equal to n, so n to the 1 over L equal to 2, something like this. So there is like approximation. Okay. So n to the 1 over L is already about 2, so calculating even higher root is higher order root is not necessary. Okay. Okay, so here we get rid of the case that this theorem doesn't handle, so the R and M greater or equal to 2. Then now we can just apply theorem and say now we draw random x, and it should give us constant probability to win. Okay, and yeah, so that's what we do. We draw random x from 1 to n minus 1. Okay, because 0 and n obviously they will just divide n. Okay? That's not coprime to n. Okay, so the first thing check is x is coprime to n. That's the thing the promise we need in our order finding. Okay, and obviously if this condition is not true, then you already win, because you find because x cannot be a multiple of n, so the GCD cannot be n. So this must be a non-trivial. If GCD x not equal to 1, this must be a non-trivial vector of n. And yeah, so you already find the non-trivial vector of n here. Okay. And yeah, so now we have everything. N is odd, has more than one prime vector, and x is coprime to n. And we just okay. I guess here is a little different. Okay, but anyway, so every x we draw, we need to check this. We want to draw different random x. Okay, so we draw random x, and then we do the actually quantum part. So this is the only part of the quantum here. Okay, so we use our quantum order finding algorithm to find the minimum r such that x to the r equal to 1. Okay, so we want to find this order here, and yeah, and then basically we want to do the GCD of x r over 2 minus 1. So if r is odd, then you are unlucky, and r is even, then you can calculate x to the r over 2. And so here's another thing to check. We need to I guess yeah, I guess when r is even, then you just calculate x r over 2 minus 1 and calculate this GCD with that. Okay. And so if you get lucky, then this will give you a non-trivial vector. And if you get unlucky, then you go back here and run through everything again. And by our theorem up there, we say the probability getting lucky here is constant. So you only need to run this constant number of times to have a pretty good probability to solve your factoring. Okay. Yeah. And that's the factoring algorithm. Any questions so far? If not, then we'll talk about factoring algorithm again. And so the above presentation is like the modern view of the factoring algorithm. So now we go back to history a little bit. So actually, so remember we talked about, so let's go here, right? So we talked about factoring algorithm as like a way to do, as like we do phase estimation on something. Okay. But actually, phase estimation algorithm is discovered after the factoring algorithm. Okay. So when Peter Shor is designing the factoring algorithm, he doesn't have an idea of phase estimation algorithm. So phase estimation is actually something Kitaev do. Okay. So here we have a funny history. So Kitaev invented the phase estimation algorithm because he heard that Peter Shor has a quantum algorithm for efficiently solving factoring, and he couldn't get a copy of the paper because he was stuck in Russia at that time. So he just came up with his own factoring algorithm, and that's why he found out that's why he invented phase estimation. But also, if we go into history even a little more, you will find out that Kitaev's phase estimation algorithm is nothing as this phase estimation algorithm. It doesn't use quantum Fourier transform, and it's more complicated. So I guess the view we presented is kind of a hybrid of two to make it easiest. Okay, and so anyway, that's a bit of history. And why we just talk about history, because we want to present the viewpoint of Peter Shor of why he how he did the factoring algorithm without thinking about phase estimation. So hopefully this gives you a little more intuition about the Shor factoring algorithm. Okay. And okay, so anyway, here is the view we presented well, anyway, so everyone knows we need to do period finding, so we focus on the period finding part. Okay, so how does Peter Shor do period finding? Okay. And yeah, so So here is a schematic of the period finding algorithm or order finding algorithm, and yeah. So we say it's a phase estimation on the multiplication oracle UX and having the eigenstate as 1 here. Okay. So and we have 0. So 0 go to those header marks. So now we have. On 1 here, we have the first register become equal superposition of everything from 0 to n. Let's say n is like 2 to the small n. Okay. And then on 2, we'll apply all the oracle here. And so this is something similar you do in your homework. In your homework, you will calculate what this state is, and is this state. And anyway, on 2, you apply ux on 1 depending on what's the k here. So if k equals 1, you apply x once, and k equals 2, apply x twice, etc. So you have x to a k, and this is actually mod n here. Okay. So maybe this is a little more clear. So mod n x to a k, and so those are the periodic thing, so maybe go back to our example, or this is a bit funny example. Okay, this example, okay, so the x to a k will be those 6 numbers cycling through each other. So yeah, so if your x is 3 and equals 7, and then you run your order finding, and x to a k will cycle through these 6 numbers, depending on the k. So k equals 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11, 12, etc. Okay, so the second register will be those 6 numbers, or those are different numbers cycling 1 by 1. Okay, depending on the k. But we usually count k from 0. Okay, so k from 0 to bigger than minus 1. Okay, and yeah. So that's the algorithm, and then we say we do phase estimation. So phase estimation, we apply QFT minus 1 here, and then we measure. Okay. But now we want to do something funny. So I want to, well, the algorithm is still the same, but I want to see the different ways. So we analyze it by kind of what do we do, like Simon's algorithm. What do we do in Simon's algorithm is that we also have some phase kickback part, but on the second register here, we actually measure it, okay, to make things a little easier. So I guess it's kind of analyzing this in different bases. So in the order finding, when we analyzing the phase estimation, we will kind of measure in the second register we kind of measure the second register in the eigenbasis, right? So we decompose it into different eigenstate and say what different eigenstate will do. So this is kind of equivalent to measure the second register in the eigenbasis, those UA spaces. Okay, and okay, but here we do a different analysis. We say what happens if we just measure the second register in standard basis. Okay, and if you measure this in standard basis, then you will get a bit ugly thing on the first register, but it's still something funny, and we'll see what it will do. Okay. Okay, measure. Okay, so I should say in standard basis, although it's kind of, or in computational basis, although that's kind of assumed in computational basis. Okay, and anyway, so on a high level measure here on what basis it shouldn't change the result here anyway, because this line here has no interaction with the first line after this part. So you can measure in whatever basis you like, and it shouldn't change the outcome probability up here. You will just give you a different analysis. And but this thinking is how Peter Shor think about this at the start. Okay. So he kind of think, well, we'll see later. So he kind of think about if we have this first part of the circuit, so we have this part, and we get something and that related to our period R, and then you find out that then we want to find what R, then you can just apply quantum Fourier transform. Okay, and I think then he invented the quantum Fourier transform to solve it. Okay. Okay, and okay. So what if we measure in second register? So now it's actually a bit complicated because of the error. So now we want to assume something that's a little bit, but just to make the notation a lot nicer. So we assume Kn is a multiple of R. Okay. And why I want to do this is because you think about what's the second register. So second register, k from 0 is x, and k from 1 is x. Sorry, k 0 then is 1, and k equal to 1 is x, k equal to 2x squared, etc. all the way to k equal to r minus 1, you have x r minus 1, and so it's cycling through this thing. And then you have k equal to r, you have x to r equal to 1, and k equal to r plus 1, then you have x here again. And so you see it divided into these blocks, and there are totally n of them. And so if n is a multiple of r, then here you have like a very nice structure where everything, so every of those different x here, you have a same number of them here. Okay? So if n is a multiple of r, then you have a total of n divided by r blocks, and each block have also one to have r different element here. Okay, so this just makes notation a lot nicer. Okay, and okay, so we assume this to just give you a showing of how things work out. Okay, so we have m divided by r blocks here. And so now you measure here, and there are different values. So those are different values will keep cycling each other, and you will get a uniform one. So you will get a uniform k that's from 0 to r minus 1, and then the second register will become x to the k. Okay, and okay, so you get k on the second register as your measurement result. But what will be your first register? So first register. So you get this result, basically you do this projection, basically do this projection, I times x to the k, x to the k, okay? And yeah, so you basically project the second register to x to the k. And so your first register will be everything that give you x to the k on second register. So for example, k equal to 1, then you will get those things, okay? So k equal to 1, not only you get k equal, so you have x to the 1 on the second register, then not only you get the k here, you also get k plus r and the k plus r, 2r, etc. So every block you will get something corresponding on the first register. Okay, and there are totally n divided by r blocks, and you will be counting, then you see the least number is k plus n minus r, or n plus k minus r. Okay, so you just yeah, you just do some counting and see there are n over r numbers here, and here we are. Okay, here we are very careful. We are keeping our normalization here correct. Okay, so we start with 1 over square root n here because you have n different k here, and you have 1 over square root n here, and now you have square root n by r because we have n over r blocks, and so here this thing actually and so this thing, there are n over r blocks, so there are n over r things here, so you should normalize by r1, and this can also seen by because the probability of getting each of those is 1 over r, and so you should get this. So you normalize away this 1 over r probability, you should get square root r in front, square root r factor up here. Okay. Okay, so the normalization is 1 over square root r1. That's nice. And so then now we just write this in non-compact form. Okay, so this is square root r1, and summation on L. Okay, so L is so we think it is r and the 2r part, and this is L equal to 1, L equal to 2, etc. Okay. So L from 0 to n minus r minus 1, so there are totally n over r different L, okay? N over r different L as we expected, and k plus LR. So this is just writing the summation in more complex form. Okay. With the L factor tell me how many are I'm adding. Okay. So this is a state that after up here before you do QFT and what you get in computational basis. And why does this state that Peter should think that he should do Fourier transform it? Because this state is actually very famous in classical signal processing. It's called post-trend. Okay. So this state looks like this. Is so this register, I don't know. This maybe X, doesn't matter. Okay, so this is like so it's called post-trend or in post-trend. Anyway, so it's a signal that has spikes that evenly spaced out. Okay. Okay. So it looks like it is a signal that has like R and R difference between that. So you have those posts or spikes that are evenly spaced out and the same height, and yeah. So you have a uniform height and evenly spaced out, and you have this kind of signal. And it's well known in classical signal processing that if you do Fourier transform on this thing, then you will get this signal. Okay, so you will get another impulse trend. So impulse trend transform back and forth. Or yeah, the input. You have an impulse trend, you Fourier transform, you get another impulse trend, and if Fourier transform back, you also get Fourier impulse trend. And but what happens is you do Fourier transform, then the spacing here is R, and the spacing here will be 1 over R. And also, something funny is so you see you have some displacement here, and so you have a displacement Ka here. But actually, when you do Fourier transform, as we'll see later, we'll see very soon. So you do Fourier transform, and this K factor actually doesn't give you same displacement here. Okay. So although you have a K factor here, so here you actually you start with 0, okay? And so you start with 0, and so actually those spikes are the S over R thing we have been seeing. So this one will be 0 over R, and this location is 1 over R, and so each one of them will be S over R. And then you will kind of ask where does the K information go to? So K information go to something that we cannot draw on this picture. Okay? So we say those spikes have the same height. But actually, Fourier transform is on convex signal, so they also have phase. Okay. So this K displacement will give like a different phase on all those spikes. Okay. And this is yeah. So the K displacement here give you the transformation of spikes. And here you have no displacement here corresponding to all the phase here are the same, right? So here the thing is uniform in either amplitude, also they have no weird phase factor between them before that. Okay. So that's about a bit of that's the classical Fourier transform intuition why we want Fourier transform to solve this thing. Okay. And yeah, so the intuition is that you get a spectrum, you get an impulse train here, and so if you get a Fourier transform, then you get an impulse train with this spacing 1 over R, and you learn 1 over R, then you basically learn R. And I guess talk a little more about information here. Okay, so you kind of want to ask why don't we just measure here, right? We measure here, and then we can kind of also learn the spacing in the R here, right? But you think about it, it's not possible because you will get a random K plus R here. But this K is also random, and guess where? I'm a little confused. Oh, okay, yeah. So you know K, but now I'm confusing myself a little bit. But I think Wait. So, okay. Sorry. We don't know k. Okay. And to know k, you need to solve something basically as hard as order finding as discrete log. Okay. So we actually know x to the k, and we don't know k. Okay. We know x to the k, but we don't know k. Okay. So we don't know k here, and so if we measure this state, we will get a random k plus r. But k is also random, so basically you just get a uniformly random state on this 0 to n. Okay. And so you get no information. But you might say, what if you get two of them? You get like two of them, then you can get like r to some power. But you can also not get that, because remember here, up here when we measure, we get a uniform random k. So you measure here, then you measure here, you get some k, and next time you will get a different k. And yeah, if r is large, then you need to get many times to get the same k to get two different impulses on the same train. Okay. And that's why we want to say we want to get with. That's why the Fourier transform getting rid of the k information here is important, because you get a random k, and yeah, the random k is something you totally cannot control. But if you can get the r information without getting disrupted by this k, then you are good. Okay, so that's why we want to do Fourier transform here. And yeah, so now we are finished this. Then let us see this intuition how it actually works out with Fourier transform. Okay. So we have this impulse train, and let's calculate the Fourier transform or inverse Fourier transform. Okay, so we apply inverse Fourier transform. Now it's just math, and we do our formula. And so let's write down everything of the sense data sense of this part stay here, this part stay here. And now we Fourier transform this thing. Okay, so we transform computational basis state. Then with summation, some numbers, so here with j from 0 to n minus 1, because we are doing Fourier transform on, is Fourier transform on big N, okay, on something from 0 to n minus 1, okay. So Fourier transform of dimension big N, and then we too have e2, okay, and it's minus 1, so e2 minus 2 pi, and it should have jk over n. So j is this j, and k is actually this number here. So k is this number here. So e to 2 pi jk over big N. Okay, so this is just Fourier transform formula. And then next we start doing things. Okay, and the first thing you do is something you always want to try is you have two summation, you want to reverse the order of summation. Okay, so we sum j first, and so we put the summation j first and the summation L next. Okay, and now we pull out the summation j. Then yeah, so we basically want to deal with summation L first. Okay, so we only leave the part that depend on L inside. Okay, and the part depend on L is this part. And then you see the jk part doesn't depend on L, so we just put it outside. So it's here. And here you kind of already see the separation of k. So k is staying here, and in some phase it's not going to be important later. And but what about the L part? So you sum L, and here we write things in a nicer form. So we L from 0 to n well minus 1 e to a minus 2 pi, and write jL, and instead of j or r over n, we put like r down here. So we have j over n minus r. So here's nothing, we just put L up here to L down here, dividing n. Okay, and yeah, so everything stays the same. Okay, and so why we want to do this? Because we want to see this kind of like summation of Fourier coefficients in terms of in a different dimension. Okay, so this thing now is thinking like it's summing over Fourier coefficient with this with instead of n we have n over r, which let's just call it n prime. So maybe I should anyway, yeah, it's n over r, and let's call it n prime. Okay, and so it's your summation L from 0 to n prime minus 1. And e to a 2 pi I j over n prime. But this thing we have seen before, right? So in our Fourier transform, this is the Fourier transform normalization we have been talking about. although you have a minus sign, but minus sign doesn't matter here. Okay, and you have this e to the 2 pi jk over n is equal to 0 when k not equal to 0, and equal to n when k is equal to 0. Okay, so here is similar. So k is actually j here. You are summing over L. Okay, and yeah, so you see n prime is like n here. So you are summing those vectors with with n prime equal to n divided by r. And so just as before, if j equal to 0, then this vector is always 1 because it's e to the 0 always. And you are summing over n prime different ones, and you got n prime. And when j equal to non-zero, then things will go over the circle thing. And so you will summing over things equal position on the circle, where the number of partitions is n prime, but anyway they sum to 0. Okay. And yeah. And so now we see that this thing, okay. So you see this coefficient is non-zero only when this thing happens. So j equals 0 modern, so j is an integer multiple of n prime, and is j here. Okay. And okay, so what happens with major j? Then we see that when j not equal to integer multiple n prime, then you have no probability of a major also getting j. And so we only have amplitude when j is integer multiple n prime, and so j is integer multiple s times n prime, which is bigger than divided by r. Okay, so j is an integer multiple of this n divided by r. Okay, for some integer n s. And so we have non-zero amplitude. What's the actual amplitude? So amplitude doesn't care about this phase, it's just phase. Okay. So you measure this whole thing, and amplitude is well the thing squared, right? Okay. And yeah, and so you measure different j, so the summation j is not important. And so you see, so when you fix the j, then what's the amplitude for that j? So that's this thing squared plus this thing absolute squared plus this absolute squared is 1, plus this absolute squared. Okay. Yeah. So so I'm talking about probability, but we're only talking about amplitude. Then is the first term square root over n, and then this thing taking amplitude is 1, like we said. So we get rid of the k information. And then the next term amplitude is n prime, and so n prime is n divided by r, so the amplitude is 1 over r, and so the probability is 1 over r. Okay, and yeah, so that's like what we get in our phase estimation analysis. We will get some s over r with probability 1 over r. Okay, and yeah, so how we get s over r is just a different way of counting. And we just say, instead of wanting this j from 0 to n minus 1, we want it from 0 to 1, or more like 0 to n to 0 to 1. And so it's just different notations. We say divide this number by n, and the thing you get is s over r. Okay, okay, so that's basically the analysis. And but this analysis, as you say, we want to make things simplifying, and so we assume n is integer multiple r. And if that's not the case, then the analysis gets very annoying. And the annoying thing, we already skip it once, and we'll skip it again. And the annoying thing is basically doing the error analysis of the phase estimation. Okay. So that's where your phase estimation don't have things on your ticks here, and you have those error probability distribution. Okay. And yeah, so when r doesn't divide n, and the accuracy analysis was similar to a phase estimation analysis here. And basically there are two ways to do it. You can say you have enough digit of error, digit of precision, and calculate how many digits you have, or you can do this constant probability to get the correct one thing, because you see we already have a lot of constant probability when we do Shor's algorithm, right? So you just do one more constant probability thing. You just do one more probability thing when you try to do the order finding, and you repeat a few more times, and you will get the correct period, etc. Okay, yeah, and we are 5 minutes early, but that's the view, that's the intuition behind the Shor's period finding algorithm. That's Peter Shor thinking about it. Okay, any question? Otherwise, we are 5 minutes early, and I think we can just stop 5 minutes early. And on Thursday, we'll now teach you about something. We talk about we'll teach you about how to use the Qiskit to write a little bit of quantum algorithm on the IBM server, and also how to run your small program on the IBM quantum computer. Okay. And I'm not sure that will take 2 hours, so maybe we'll also start talking about Grover's algorithm on Thursday. Okay. So yeah, no question. Then let's stop early, and see you on Thursday.